Hello, everyone. So I'm Mike. I'm working as a research assistant together with Justin on the StarFOX experiment. So StarFOX is an acronym for Starling Formation Flying Optical Experiment. So it's an on-orbit demonstration of distributed angles-only navigation for spacecraft swarm. And so in the StarFOX Plus experiment, we basically want to add some new features and improve some features too. So in this presentation, I'll basically cover the features that I've been working on this quarter. So first of all, starting with for people that don't know exactly what StarFOX is, basically what it is. So it relies on a software package called Artemis, which stands for Absolute Relative Trajectory Measurement System, which basically means relative and absolute orbit estimation of the spacecrafts which are part of the spacecraft of the swarm. And it's comprised of three key modules, being the ones in green, so the IMP, which is image processing, BOD, batch orbit determination, and SOD, sequential orbit determination. And then there's also two key other components, which is the vision-based sensors and the intersatellite link. So from the vision-based sensors, the software package gets the sensor data, which it's using to make estimations. And then the intersatellite link allows it to share the measurements between the members of the swarm. So the IMP, it's processing the images. So it's basically identifying the objects that are in the image, which can be stars or other starling satellites, and potentially also other objects, which is important for later. And so then it's sending those measurements to the sequential orbit determination, which, using its current estimate of the orbits, makes the measurement updates. So in the core of this, it's an unscented Kelvin filter. And then also important, so as you can see, the IMP is the only one which can send things over the ISL to the other spacecrafts, and SOD is the only one which can receive information from other spacecraft over the ISL. And so the last module is the BOD, which I haven't really worked with, but it's essentially used to initialize the sequential estimation of the SOD. Okay, so with that background, so I'll go into the first feature, which was for the SOD. So besides orbits estimation, we're also interested in now estimating other auxiliary states, among which the sensor bias. So basically, the way that it's implemented is according to this schematic. So basically, the IMP receives an image which is biased from the sensor. And so when it's extracting the bearing angles from this image to the objects that it's identified in the image, they will be biased. So it thinks that the object is somewhere else compared to the ground truth. And so the way that the bias is estimated is that each spacecraft estimates its own sensor bias. And so when it's receiving measurements from IMP, it'll basically add its estimates to the measurement model. And so it does estimating the bias. And then this estimate is sent to the IMP, reason being that the IMP is able to send these estimates over the ISL. And so the idea here is that if it's receiving measurements, if the SOD is receiving measurements over the ISL from other spacecrafts, in that case, it also receives the estimated biases of that spacecraft. And so what it does is basically it'll add the bias that it receives over the ISL to the measurements that it's receiving over the ISL, and then it's using that to update the estimates. And yeah, that's basically the idea. So each spacecraft in the swarm has its own estimates of its biases, And so when it shares measurements to other spacecraft, it also shares the estimate of its own bias that it has, so that the other spacecraft can use this bias to then correct the measurements that it's receiving. Okay, so then some experiments. So the first experiment is using this configuration. So there's one spacecraft, which is the observer, and 3 of them which are being observed, so our targets. So spacecraft 4 is taking measurements of spacecraft 1, 2, and 3. And basically how the experiment is set up is that there was a bias introduced artificially in the measurements of 20 arc seconds. And so what this means is that we want to see basically that the measurement error is distributed according to a mean of 20 arc seconds and whatever noise is introduced to the measurements too. And so in this table, the measurement statistics are shown. So basically, this is the measurements taken by observer 4, so spacecraft 4, of targets 1, 2, and 3. And so these are the bearing angles, azimuth, and elevation. And so on the left here, you can see the raw measurements which are taken. So the measurement errors, so this is the difference between the measurements and the ground truth, are distributed with a mean of 20 arc seconds and then a noise of 10 arc seconds, which is as it's intended. And then the corrected one here on the right is basically the statistics after the bias estimate is subtracted. So basically the unbiased measurements. So you can see that most of these at least have become like much closer to 0 as compared to the raw measurements. And then here you can see the actual bias estimation over time for both the azimuth bias and the elevation bias. And so the blue line indicates the estimate over time, and the black line indicates the true bias that's introduced. And the shaded area is the uncertainty. So you can see that both of them converge to the true bias. Then in another experiment, I basically did the same, but now simulating only the spacecraft, the just spacecraft, which only has targets spacecraft 1 and 2. So this is one target less than before. And so in this case, the results are not as good. So on the first table, we have the bias estimation disabled, so there's no estimation performed. And so you can see that the measurements are still, the raw measurements are still distributed as intended. But then once the bias estimation is enabled, the raw measurements are now distributed not as they should be. And the corrected ones are even worse. So this basically indicates that the bias estimation has not converged. Which is something that needs to be further investigated. Then in another so that's like before any processing. Yeah. Well, yeah. So this is also something that I discussed with Justin, because according to this, there seems to be a dependence on what happens in SOD, and it's reflected in the raw measurements, which is, it's not really supposed to happen, of course. So it's something that needs to further be looked at. So I include. So that I'm not sure about. Yeah, exactly. So I've also discussed this with Justin, but yeah. Because ideally these would be the same, so that the raw measurements would. That's also why I included this table, to show that there's something that's not really correct, because these should just be as they are, like unaffected. Then in the third experiment, now we look at multi-observer spacecraft. So in the previous ones, there was only one spacecraft being simulated, or one spacecraft that's an observer and running the Artemis software. Now, in this case, there's two observers, and they have an inter-satellite link, so they share the data. Now, in this case, so again, first considering no bias estimation to kind of like get a starting point of seeing if everything is working as intended. But then when I look at the statistics again, so they should be distributed with 20 mean and 10 standard deviation. But so the measurements are not really looking great. So again, this is something which should further be looked at as to why this is happening. Probably somewhere a little error in the code. But yeah, basically I'm working on fixing that too. And so yeah, so for further work on this specific feature, it's basically what I mentioned. It's investigating why the difference between the 2 and the 3 targets performance, and then also resolving this multi-observer measurement. And then once that's resolved, it's basically running more experiments with different configurations, different spacecrafts, different distances, different lengths between the spacecrafts. And then moving on to the next feature, which was for IMP. So the image processing. So like I mentioned before, when we receive an image from the VBS, we identify the objects in the image, which can be stars or other starling spacecrafts, but they can also be objects which are just other things in space, right? So basically the idea is here that we can use the space, the catalog, which has like a bunch of objects in space, listing the orbits and other data of these objects. And so, yeah, so the idea is to use this catalog. So we send it to the observer. And then when we take an image at a certain time, we propagate the catalog to the image time. And then, so as I said, IMP identifies the objects in the image. From the start, it gets the attitude of the spacecraft, and then we get the unit vectors of between of the observer to these objects that we identify in the image in ECI, and then from the objects that we propagated from the catalog, we get the same unit vectors in ECI, and so basically, what this gives is another set of measurements that we can use to update our orbit estimates. So we basically want to match the object that we identify in the image with an object from the space catalog, and then use this information where the image is the measurement and then the space catalog is the measurement model. And so the blocks in green are already features that are implemented in IMP. That's what it's basically doing. So then basically for the propagation, we're using the SGP4 propagator. And then so I've gotten a implementation in C++ to work. So this is kind of like a verification. So this is showing the starling spacecraft at a certain point in time, propagated, and then these are compared to GPS data, and these are the errors between the propagation from the SGP4 propagator and data from GPS. And so these are the errors that we get. Which, yeah, seems to be good. And so, yeah. So that's working. And so basically now what's next is to integrate this into the IMP module. So we want to receive the catalog in the IMP module and then propagate these objects as intended. And then further just implementation of what I covered earlier, but then in the IMP module in codes. And then eventually the idea is to, of course, use this information to improve the estimate in the SOD module. And then, so this is kind of the basic idea, the basic implementation. But of course, up till now, nothing has been distributed or like nothing has interacted with other spacecrafts. So the idea is basically to then further extend upon this idea with trying to share this information between the different spacecraft in the swarm too, and get some useful information from that. Also, another feature is to track the object, and so for longer, so that we have it in frame for longer amount of time. But that's kind of like this part is kind of the main idea that I'm working on right now. And yeah, that's it.